This is lecture 29 of Physics 210A, thermal physics. And in this lecture, we are going to discuss the classic Einstein's paper on the concept of light quanta, what we now know as photons. The paper was published in 1905 and its translation is available, so the references are A, B, Arons and M.B. Peppard in American Journal of Physics, volume 33, page 367, 1965, and this is a translation of the original paper by Albert Einstein in Annals der Physik, volume 17, page 132, 1905. This is the paper on which Einstein was awarded the Nobel Prize. So let's just recap what we know so far. One, we know Wien's formula for spectral density of black body radiation, and I'll use the notation in this paper, and using that I'm going to write U nu T is equal to some alpha nu cube e raised to minus beta nu over T. Notation used is similar to that in the translated paper. We also learned about statistical interpretation of entropy, according to which the entropy is given as K Boltzmann, some constant now we know is K Boltzmann, log of omega E and other macroscopic parameters of the system. Third, we found omega for a given volume and energy for an ideal gas. And for a given energy, we found that omega was proportional to V raised to n, where V is the volume. And therefore, if volume changed from V1 to V2, this we knew from thermodynamics also as well as from statistical interpretation, S2 minus S1 was equal to n Kb log of V2 over V1. With this, now we are ready to discuss Einstein's presentation, and what he did was he conceptualized the existence of light quanta by comparison with an ideal gas, but that would have been just a theoretical thing to do. So he went a step further and then used this concept to explain certain experiments. So that actually showed that his way of thinking that radiation can be thought of as if it's made up of particles, light quanta or photons. So that he conceptualized and showed it, that explains certain experiments which were not explained otherwise. And one of them is the photoelectric effect. So let's start with the exact formula for u nu t, and it is u nu t is equal to some constant 8 pi h over c cubed nu cube over e raised to h nu over kBt minus 1. This is the exact formula, Planck's formula. Now for t tending to infinity, and that is nu by t becoming very small, this goes over to 8 pi h over c cubed. H also goes away, nu square kBt, and that is Rayleigh-Jean's formula. This can also be derived based on equipartition theorem. Now, for the Rayleigh-Jean's formula to be valid, since t is going to infinity, this formula is valid for intense radiation, very intense. The intensity is very high. On the other hand, if t goes to 0 so that nu over t becomes large, and that means very weak radiation, intensity is very low. This formula u nu t becomes 8 pi h over c cubed nu cube e raised to minus h nu over kBt, which I am going to write as alpha nu cube e raised to minus h nu over kBt, which is nothing but Wien's formula. So Wien's formula is valid for weak radiations, and so at small temperatures, and nu over t is large because t is small. So this, since this is weak radiation, this can be compared with ideal gas, which we will do. Now, what does Einstein do? Einstein's program is calculate the entropy of radiation for a given energy E and compare its change with volume with that for an ideal gas. And then similarity between the two indicates that there are n light quanta equal to E divided by h nu. That is, each quanta is quantum or photon carries energy h nu. So that's his program. So for that, he first write, to begin with, step 1, write S equals, the entropy equals, volume times entropy per unit volume, and for that I am going to write phi, which is going to be spectral phi, which is going to be a function of u nu d nu. So phi nu d nu is the entropy of radiation between frequencies nu and nu plus d nu. Obviously, the corresponding energy of the radiation in this between nu and nu plus du nu is going to be in phi nu, u nu d nu times the volume. And the total energy E is V integral u nu d nu, 0 to infinity. So thus we have introduced certain definitions. So we have introduced spectral distribution of the entropy. Now this step I am not going to do, but just state it. Maximization of entropy S with respect to u nu for a given E total. E total, remember, is integral u nu d nu, leads to partial derivative of phi nu u nu with respect to u nu equals constant, which I am going to call lambda, following the paper's notation. So this is a constant, which is lambda. Now, next step, I am going to relate this to the temperature. I know 1 over T is equal to partial S partial U at constant V So this is going to be, total S is going to be V integral d phi nu d u nu. I'm changing u nu by delta nu, integrated over d nu, divided by change in u, and that's going to be total delta u times v. Now, since del phi nu over del u nu is lambda, this can be taken out. So I get 1 over t equals v lambda integration delta u nu d nu divided by delta u total v. Now we can cancel certain terms. V cancels, delta u total cancels with this. So this is equal to lambda, which is nothing but del phi nu over del u nu. So I get the final result that 1 over t is del phi nu over del u nu. I'm going to use this to find phi nu, use this to find phi nu, u nu. Remember what we are after. We are after the entropy and its change as volume is changed. So let me just recall that we are after S and delta S for nu and nu plus d nu radiation in that range. So that's what we want to do. So what we have found is that 1 over t is equal to partial phi nu partial u nu, and now we are going to use Wien's formula to express 1 over t in terms of u. Recall that Wien's formula says that u nu is equal to alpha nu cube e raised to minus beta nu over t. And therefore, you take log on both sides, log u nu over alpha nu cube is going to be minus beta nu over t, or 1 over t is equal to minus 1 over beta nu log of u nu over alpha nu cube. This then gives, use of this here, gives d phi nu du nu is equal to minus 1 over beta nu log of u nu over alpha nu cube. Now integrate this using integral log x dx equals x log x minus x. Then we get phi nu is equal to minus 1 over beta nu. Inside I am going to get u nu log of u nu minus u nu minus u nu alpha nu cubed. And therefore, this can be written as minus 1 over beta nu, u nu comes out, log of u nu over alpha nu cubed minus 1. That's the spectral density of entropy. So now, if we calculate entropy for radiation between nu and nu plus d nu in volume capital V, we are going to get S equals V phi nu d nu, which I can write as minus u nu d nu V using the formula derived earlier divided by beta nu, and inside I have log of u nu over alpha nu cubed minus 1. Now, the energy E in this range between nu and nu plus d nu is integral u nu d nu V. Well, integral is only over nu to nu plus d nu, so this can be written as V u nu d nu. And therefore, S is equal to minus E over beta nu. Inside I get log of E over, I am substituting for u nu, alpha nu cube d nu V minus 1. This is the expression for entropy at energy E. Now recall that beta is nothing but h over kb from Planck's formula. So now, change the volume of the cavity containing radiation without changing its energy from V1 to V2. So this is similar to free expansion of an ideal gas from V1 to V2. Remember, in free expansion, there is no change in the energy. And then you get here S2 minus S1 is equal to E divided by beta nu log of V2 over V1. So what we have shown through all this is that there is a cavity and inside there is this radiation. If you consider radiation between nu and nu plus delta nu, and then you can add and the whole thing will be the same, then you have S2 minus S1 equals E divided by beta nu times log of V2 over V1, which I can also write as, using beta, equals h over kb. kb E over h nu log of V2 over V1. For an ideal gas, containing n particles and undergoing free expansion from V1 to V2, we have S2 minus S1 equals Kbn log of V2 over V1. And this suggests that low intensity radiation can be thought of as consisting of n particles with each particle having energy h nu, and therefore, which implies that n is going to be E divided by h nu. So, h nu is the energy of this light quantum. Einstein went further and looked at its statistical treatment. Let me do that also, which is quite simple. And that is, if you go back to lecture 28, we had, for an ideal gas, the number of states of volume V and energy E was equal to some constant V over n times E over n raised to 3 by 2 raised to n. So, proportional to V raised to n. And this implied that entropy was proportional to n kb log V for a given energy E. In the present case, we have S2 minus S1 equals Kb E over h nu log of V2 minus V2 over V1, which can be written as Kb log of V2 over V1 raised to E over h nu. And this shows again that entropy is calculated as if there are E over h nu particles of radiation in the cavity. So, this was again an evidence that I have this radiation which can be considered as composed of these particles, each with energy h nu, and total number of particles is E over h nu. Of course, there is a note here that the statistical treatment of photons was later done by S.N. Bose, who came up with this statistics that photons follow, and which is now known as Bose-Einstein statistics. Now, if Einstein stopped here, this would have been a theoretical exercise. If Einstein stopped at this point, then this whole exercise is a fantastic theoretical construct. With no evidence of radiation consisting of particles each of energy h nu for frequency nu. So what he did, he went further. So Einstein then applied it to problems that could not be explained by electromagnetic theory, employing waves. So the three problems he attacked were: number one, Stokes' rule, whereby the radiation scattered from molecules has lower frequency. Two, what he called emission of cathode rays on shining light on them. On metals, what is now known as photoelectric effect, and this was the Nobel Prize. But you see, this was only a part of the whole concept of photon. And third was ionization of gases by UV light. I'd like you to read this from the reference paper. So with this, I conclude my lecture. The concept of quanta of light was introduced by Einstein using entropy change of radiation on changing the volume of cavity containing it. And the concept was applied to explain certain experiments. So, in this paper, in this lecture, we have discussed this classic work of Einstein. Thank you.